Conditional probability. Suppose I roll a fair die once. Let A be the event that the upturned face shows a 5, and B the event that this face shows an odd number. Are A and B independent events? Let's compute the probability of A intersect B. This is the probability of 5, an odd number. It's the probability of the single point 5, which is 1/6. We need to compare that with the product, the probability of A, times the probability of B. A has probability 1/6. B has probability 1/2. This is 1/6, this 1/2, which means that they're not equal, and therefore they are not independent of one another. Now suppose I roll a die so that you can't see it. If I look at the upturned face, and I tell you that that upturned face shows an odd number, now how probable do you think is the event A? There are 3 odd numbers, 1, 3, 5. You have no reason to believe that any one is more likely than another. So if you were to guess the probability of 5 in the light of this new information, then I think you would guess 1/3. This is an example of a calculation of conditional probability. Here's another example. A certain university has 30,000 students, of whom 14,000 are female. 9,000 of the students are math students. The university population is depicted in this figure, and the blue side of this line of demarcation consists of the male students, and on the left-hand side we see the female students. The math faculty is naturally in 2 colors. It turns out that there are 9,000 math students altogether, of which 3,000 are female. And in total, we know how many male and female students there are in the university at large: 14,000 female, 16,000 male. Are A and B independent events? To determine this, once again, we determine the probability of A intersect B and compare with the probability of A times the probability of B. The probability of A intersect B, this is the probability that a randomly chosen student is a female and a math student. There are 3,000 female math students in a total population of 30,000 students, so that's equal to 1/10. On the other hand, the probability that the student is a female, or the probability of the event A, is equal to 14/30. And the probability that the student is a math student, the probability of the event B, is equal to 9/30. P of A intersect B, in this case, is not equal to P of A times P of B. And so these 2 events are not independent, they are dependent. Now let's suppose the student that we selected at random is known to be a math student. In this case, what's the probability that the student is female? If the student is known to be a math student, then they must be drawn from this portion of the population, the portion in pink. That portion consists of 9,000 math students, of whom 3,000, or 1/3, are female. So the answer is 3/9, or 1/3. This is another example of a conditional probability calculation, where we again determined a probability in the light of some additional information, in this case that the student was a math student. The definition of a conditional probability of an event, A, given that another event B occurs, is denoted by the probability of A bar B. And that line, that bar, should be read as given, the probability of A given B. And this equals the probability of A intersect B divided by the probability of B. Of course, I'm only permitted to divide by the probability of B, provided that P of B is a positive, non-zero number. Here's a result. Suppose A and B are 2 events, both of which have positive probability, which is usually the case in this course. Then A and B are independent if and only if the probability of A is equal to the probability of A given B. This is another way of saying that the event B, if you're told that B occurs, this would make no difference to the probability that you assign to the event A occurring. The unconditional probability of A is the same as the conditional probability of A given B. Equivalently, they're independent on reversing the role of A and B if the probability of B is equal to the probability of B given A. Let's verify this result. Assume, to begin with, that the probability of A given B is equal to the probability of A. Let's write out exactly what the probability of A given B is. It's the probability of A intersect B divided by the probability of B. And that's equal to the probability of A. And on the third line, we multiply both sides of this equation by P of B, and we obtain P of A intersect B equals P of A times P of B. This is the definition of independence of the two events A and B. We conclude A and B are therefore independent. Notice that in passing from lines 1, 2, and 3, all I did was multiply by P of B on both sides of an equation. I can just as easily begin with line 3 and divide by P of B on both sides, working backwards to line 1, which shows that independence is exactly equivalent to the statement P of A given B equals P of A. Here's an example. I roll 2 fair dice. If the total on the 2 dice is less than 5, what's the probability that both dice are odd? There are 2 events at play in this problem. B is the event that the total is less than 5. We can write that event out. It's of the form 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 3, 1. There are a total of 6 points in the event B, and so the probability of B is 6 over 36. What about the event A? The event A says that both dice are odd. It's easy to see that the event A contains a total of 9 points. The probability of A is 1/4. What about the event A intersect B? A intersect B consists of those points in both A and B, namely the points in B such that both are odd. That's easy to determine. It's 1, 1, 1, 3, and 3, 1. So the probability of the intersection is equal to 3 over 36. Now we're in a position to calculate the probability of A given B. What information were we given? If the total on the 2 dice was less than 5. That's the given information. We're given the event B. So this is equal to the probability of A intersect B divided by P of B, or 3 over 36 divided by 6 over 36, or 1/2. Three-student example. Jack, Jill, and Justin each take a driving test. Jack has a 70% chance of passing the test. Jill has a 90% chance. Justin, who's convinced that red lights are simply guidelines, has a 50% chance. If exactly one of the 3 students passes the test, what's the probability that it was Jill? There are 3 events of interest here. One, that Jack passes. Let's call that event A. The probability of A is 0.7, and the probability that he fails is the probability of A complement, which is 0.3. B is the probability that Jill passes. P of B is 0.9, P of B complement, 0.1. C is the event that Justin passes, and the probability of C is 0.5. The probability of C complement, also 0.5. The event that we're interested in is the event that exactly one of the 3 passes. And that can be written as the sum of the probabilities of 3 mutually exclusive events. Either Jack passes, or Jill and Justin fail, or Jack fails, Jill passes, and Justin fails, or Jack and Jill both fail, and Justin passes. And the probability of the first of these, that Jack is the only one who passes, is 0.7, probability Jack passes, times the probability that Jill fails, 0.1, times the probability that Justin fails, 0.5. We can similarly calculate the other 2 terms, and when I add up those 3 terms, I obtain 0.185. So that's the probability that exactly one of the 3 passes. D is the event that we wish to condition on. Given that one of the 3 students passed, what's the probability of the event B, that the student that passed is Jill? What's the probability that Jill passes and exactly one student passes? That's the probability of B intersect D. 0.3, the probability that Jack fails. 0.9, the probability that Jill passes, times 0.5, the probability that Justin fails. That's the numerator in the expression for the conditional probability. The denominator is the probability of the event D, which we've already computed, and it's 0.185. So that ratio, 0.73, is the probability of B given D. It's the probability that Jill passes if we know that exactly one of them passed. The multiplication rule. For any 2 events, A and B, the probability of A intersect B is equal to the probability of A given B times the probability of B. Of course, we can reverse the role of these 2 events. The probability of A intersect B is also given by the probability of B given A times the probability of A. This is easy to show. If I take the right-hand side of the first equation, the probability of A given B times the probability of B is the probability of A intersect B divided by the probability of B, all times the probability of B. And because we both multiplied and divided by P of B, this turns out to be simply the probability of A intersect B. You can use the same argument to show the reverse direction, the second of these equations. Sometimes it's helpful to think of the multiplication rule in a chronological sequence. For B and A both to occur, B occurs with probability P of B. Then, given that B occurred, A occurs with probability P of A given B. Here's an example. In a certain company, 50% of the employees are female, 20% of the female employees are to retire within the year, and 30% of the male employees are to retire. An employee is selected from that company at random. Let's begin by laying out some useful notation. Let's call R the event that the randomly chosen person is about to retire, and F be the event that that person is female. F complement, event that that person is male. Let's write some of the information that we've been given. We've been told that of the female employees, 20% are about to retire, which is to say that probability of R given F equals 0.2. We're also told that the probability of R given F bar is 0.3. Now we're in a position to address a few of these questions. The first question, what's the probability of F intersect R, female and retiring? From the product rule, this is the probability of R given F times the probability of F, which is 0.2 times 0.5, or 0.1. The second question asks, what's the probability that the selected employee is male and about to retire? The probability of F bar intersect R. Again, using the product rule, that's the probability of R given F bar times the probability of F bar. And this is 0.3 times 0.5, or 0.15. We'll continue with this problem. The next question asks, what is the probability that the selected employee is about to retire? What's the probability of the event R? The event R can be decomposed into two mutually exclusive parts, R intersect F and R intersect F complement. We've just determined the probability of each of these two pieces. They're 0.2 times 0.5 and 0.3 plus 0.5. So when we add them together, we obtain 0.25. Finally, the last question, 4, asks about a conditional probability. The probability of F given R. The probability that the employee is female, given that they're about to retire. This is equal to the probability of F intersect R divided by the probability of R. And we've now calculated both of these two quantities. Probability of F intersect R is 0.1. Probability of R is 0.25. And so the ratio is 0.4. The law of total probability. Suppose we have a sample space which is represented by the box in this picture. That sample space has been partitioned into mutually exclusive sets. For example, B1, B2, up to B5 in this case. 5 mutually exclusive sets form a partition. Assume they all have positive probability, and their union forms the whole sample space. That's what we mean, in fact, by a partition. Then we can determine the probability of any event A by adding together the probability of the events A intersect Bj. For example, the probability of A intersect B1, which appears to be 0 in this case, the probability of A intersect B2, probability of A intersect B3, A intersect B4, and A intersect B5. The sum of those probabilities gives us the probability of A. This is the law of total probability. Bayes' theorem uses that law, the law of total probability. Bayes' theorem is used when we have a partition of the sample space, as we did for the law of total probability, and we're given the probabilities of the sets forming the partition, P of Bj, and the conditional probabilities of some event A given Bj. We'd like to turn the conditioning around. We want to determine the probability of a given set Bj conditional on the event A. P of Bj given A. That's given to us by the usual formula, the probability of A intersect Bj, divided by the probability of A. Bayes' theorem is determined by using the law of total probability in the denominator to determine the probability of A, and the product rule to determine the numerator, the probability of A intersect Bj. So the proof proceeds, first, by defining the conditional probability of Bj intersect A divided by the probability of A, then expanding the denominator into a sum of the probability of mutually exclusive pieces, and then using the product rule in the numerator. Finally, in the last step, using the product rule again in the denominator to give us the sum of the probability of A given Bi times the probability of Bi. This is Bayes' rule. Here's an example you can try on your own. The same three people, Jack, Jill, and Justin, take a driving test. We have the same probabilities as before of them passing, but now we're told that exactly 2 of the 3 students passed the test. What's the probability in this case that Justin was one of those 2 students who passed? You should pause for a moment and try and solve this problem on your own. Solution. Let A be the event that Jack passes the test, B the event that Jill passes, and C the event that Justin passes the test. Suppose D is the event that exactly 2 pass the test. Then we can write D as a union of 3 mutually exclusive events, 3 possibilities. The first, A intersect B intersect C complement, represents the event that Jack and Jill both pass, but Justin fails. Similarly, the second, A intersect B complement intersect C, represents the event that Jack passes, Jill fails, and Justin passes. And because these 3 possibilities, each of which represents one of them failing and the other 2 passing the test, are mutually exclusive, we can determine the probability of the event D by adding together the probability of these 3 possibilities. Let's look at the probability of the first, A intersect B intersect C complement. These 3 events are independent of one another. So to get this, we multiply the probability of A times the probability of B times the probability of C complement. And of course, we do exactly the same with the other 2 possibilities. When we replace these probabilities by their numerical value, this becomes 0.7 times 0.9 times 0.5 plus 0.7 times 0.1 times 0.5 plus 0.3 times 0.9 times 0.5. The numerical value of that sum, 0.485. But we were asked for a conditional probability, the probability that Justin passes given the event D. This is, by definition, the probability of C intersect D divided by the probability of D. C intersect D can happen in 2 ways. Justin passes, but either one of the other 2, Jack or Jill, may fail. So that event is determined by adding together the probability of those 2 possibilities in the numerator. And in the denominator, of course, the probability of D, 0.485. When we evaluate this, it's 0.35. You'll notice that this conditional probability is different than the probability that Justin passes given no information. That probability was 0.5. But given that exactly 2 people passed the test, the probability Justin was one of them is only 0.35. Here's a Java applet, again taken from the University of Utah Java applet bank. And we see a sample space, in this case a square, with 2 events in it, the event A and the event B. On the right-hand side, you can see the probability of those 2 events. A has probability 0.189 and B probability 0.142. And the probabilities are essentially the area of these rectangles for A and B divided by the area of the whole sample space. And so probability in this example is indicated by its area. You also see that there is some intersection between the events A and B. In particular, for example, this region, the intersection of A and B, looks like it's about 1/2 of the event A. We've seen that the probability of the event B is quite small, 0.142. Let's run the experiment and see whether B occurs. This point falls outside of B, in fact outside of A and B. It did not occur. Once again, neither A nor B occurred. This time A occurred, B did not. Neither A nor B. Again. Once again, A occurred, B did not. Again, an event in A, but not in B. And on the right-hand side, we're keeping track of the relative frequency, the relative number of times that a point falls inside of A, inside of B, and so on. Let's run it for a large number of times. Let's run it for 100 times and see what happens. One thing you'll notice is, of course, there are a relatively small number of points in B itself, about 14%, well, 13%. But let's suppose you're told that A occurred. In other words, you restrict attention to this shaded region. What you'll notice is that approximately half of those points are in the set B. In fact, well, I guess, given that the point falls in the event A, it looks like about 40% of them fall inside of B. And that's this frequency over here. Although of A, the intersection with B constitutes about half of the area of A, we observed a relative frequency of around 39% of points that are in B and A divided by the total number in A itself. Let's run it for on more occasions and see what happens. In fact, let's run it 1,000 times. And once again, we compare the probability that a point falls in B if we know that it falls in A. And it looks like of the points in A, approximately half of them are in A intersect B. Well, indeed, the frequency of that is this number, 0.489, about 49%, which is extremely close to the theoretical probability of B given A.